Hi, I'm Dr. Bob Hogg, and in this video I'm going to try to give you a feeling for what a p-value is. Now, a bit of a disclaimer before I start, in that the idea behind this is to look at a very simple example and to try to make it as easily understandable as possible. So I've taken a few liberties, especially around about the maths involved, so you'll probably be pleased to hear that maths will not really come into it at any point. But as I said, I've taken a few liberties in terms of some of the examples that I'm going to show you. So let's get on with the concept, and I really want to have a look at this p-value, and in particular what this mythical 0.05 actually means in practice. So to do that, we really need to go back to why we need to run what we call a hypothesis test. And here are some definitions which you might have seen already and their explanation. What generally we do in terms of a hypothesis test is we want to know some information about a certain population, in other words, a parameter. Now, it might be that this population is very large and it will be totally impractical to take measurements, for instance, on the entire population. So that what we tend to do is to take a sample, and that sample gives us an equivalent value which we call a statistic. And it is this difference between the parameter and the statistic that we have to consider. There will likely be error between the parameter, which is what we want to know about, and the statistic, which is what we can actually see in our data. So I've put this into this diagram here. We've essentially got this sample statistic, which is what we get to know through taking our measurements on our sample, and what we want to know is our population parameter, which is what we're really interested in with regards to our research question. But there is some error associated with this estimation, and this usually has two main parts to it: bias, which I'm not really going to consider, and the most important thing here is the chance variation, which is what links to the p-value itself. So effectively, what we do a hypothesis test for is to look at whether or not any difference we see between effectively our population parameter and our sample statistic is likely to be due to sampling error, or is there something else going on. And the difference between the sample and the population, if it can be explained by the sampling error, or there does not seem to be some sort of treatment effect, for instance, in some sort of experiment, then this is what we define as the null hypothesis, and this is always the starting point for a hypothesis test. What we then do is we use gathering of data and the analysis in programs such as JASP to see whether or not any difference we can see is too large that we can accept this null hypothesis. In other words, is the difference between these two values so great that we can't really assume that it's just due to sampling error? And this is our alternative hypothesis. Based on this, we have a definition for what a p-value is, and p stands for probability, and this is the probability of seeing the data you have or more extreme, given the assumption that the null hypothesis is actually correct. So this is going to be quite important, and we're going to be coming back to this when we do a little experiment in a short period of time on to try to sort of show this effect. Now, as I said, we do have some definitions here, and again, the p-value, which often is illustrated as a significance value in some software like SPSS, is giving us an indication of whether or not we can accept the null hypothesis explanation of any differences. Now this again is effectively a convention. The 0.05 is simply a convention, and this I think is what causes a lot of confusion, because effectively it says there is a line in the sand. On one side we accept the null hypothesis, and on the other side we accept effectively an alternative hypothesis. It is best to assume that this is not a line, and we should be saying something like we can accept the null hypothesis at a 0.05 level, or a 0.01 level, or a 0.000 level. So again, try not to think of this 0.05 as I said as a line to which the software will give us a definite decision. Again, it's just a probability. So effectively we work on the premise based on this convention that if the p-value is greater than 0.05, then we're going to accept the null hypothesis, and if it is less than or equal to 0.05, then we're going to say that the alternative hypothesis is the more likely explanation for our data. So that was a bit obtuse, so I think I will look at an actual experiment which I'm hoping will clear things up a lot more. So what we're going to do is we're going to do a very simple experiment. This is where I've taken a few liberties, and that we're going to use something that you should all be familiar with, and that's a coin. In other words, we can flip a coin, and in this particular case we can flip it 100 times, and we'll then run a hypothesis test based on that experiment. Now, I'm hoping everybody is fairly happy with the statement that if this is a fair coin, then the probability of getting a head will be 50% or 0.5. So that's for an individual experiment of flipping the coin once. We're going to flip it 100 times. Each time it's going to be an independent test, and we're going to add up the number of heads and consequently the number of tails in that experiment. So if we go back to our definition of a p-value, then we need some definitions. First of all, we need a null hypothesis. So the null hypothesis in this particular case is we have a fair coin. And then we need some data, and that data is going to be a result of the experiment of flipping the coin 100 times and the number of heads you actually get in that experiment. So the question is, if it's a fair coin, what would be the number of heads you would expect to see if you flipped the coin 100 times? Now, the most likely, based on mathematics, result from that would be 50 heads and 50 tails. Out of interest, do you know exactly what the probability is of getting 50 heads and 50 tails? It might be a little bit smaller than you think. In actual fact, it's about 8% of the time. Now, to do all of these number calculations, what I've actually got is found a nice little calculator on the web. And so if we go and have a look at that, then that will give us some numbers to work with. So here is the calculator, and you can see you've got the number of flips, you've got the number of heads that we're looking for, and the probability of heads, which we'll assume it's a fair coin. Again, we assume the null hypothesis is correct, which means the probability of a head is 0.5. And I'm going to look at the type of probability being at least X heads. Now remember the definition of the p-value. Go back in the video if you're not sure. It said that result or more extreme when we're defining the p-value. And if, for instance, I run this calculator, just press on the calculate button, you'll see at the bottom here, it will tell us what we know, that the probability of getting at least one head is 0.5. In other words, the chance of success is 50%. Okay, so the question is, what happens if we increase the number of flips to 100 and we say 50 heads? Now remember, we're looking at at least 50 heads, so in this particular case this includes 50, so you might be a little bit surprised at what the result is, and it's actually about 54%, but don't worry about that at the moment. But that is saying if we flip the coin 100 times and we get 50 heads, it would be around about what we would expect, close to 0.5. Now the question I'm asking is, what about if we got 51 heads? Would you be surprised? If we put 51 in here and redo the calculation, then we get this probability of 0.46. Now would you be surprised at 50 heads, 51 heads, or shall we say 49 heads, which would be the equivalent on the other side, in other words 51 tails? I suspect you wouldn't be too surprised at that, just because we're flipping the coin 100 times and we have this chance variation which I showed you in that first diagram. But what about 52? So now the probability is starting to go down a bit. But again, 52 and 48 tails wouldn't be that surprising. My question is, how low would this value have to be before you started to doubt the null hypothesis? And the null hypothesis is that the coin is a fair coin. So let's do the experiment. What about 53? Still happy? Probability is 0.3 or 30%. What about 54? It's starting to go down. In other words, it's starting to be less likely if it's a fair coin. What about 55? Now it's getting quite low, so this is getting quite unusual for a fair coin. Let's go further. 56 down to 0.13 or 13.5% in this case. What about 57? Again, now we're actually at 9% or 0.09. 58, 0.06, and 59, 0.04431 or 4.431%. Now, have a look at this value, 0.044. That's pretty close to 0.05, which is basically that mythical value we use by convention in statistical tests. So what we're saying is if we get a value below 0.05, that is the equivalent of saying 59 heads after we flip the coin 100 times. So have a think about that, and think about whether or not, when you're doing some sort of statistical tests, whether you would be happy with a p-value, or more accurately we'll call it an alpha value, which we can set at any value we like, of 0.05, when it is effectively the equivalent of saying 59 heads out of 100 flips. Now think about that in terms of, for instance, a medical experiment. If we're looking at, for instance, whether a drug which has awkward side effects, whether or not you'd be happy to take that drug based on a p-value of 0.05. Maybe not in certain circumstances, and so we might want to have a smaller p-value. But what does that mean in practice? Does it mean 0.01 or 0.001 we'd be happy with? Again, we can use this calculator to find out what that means in our coin flipping example. So for instance, if we go to 60 heads, it's 0.02. 61, now we're down at 0.01. Probably better, 0.01049. So if we've got a p-value of 0.01, we're talking about 62 heads in 100 flips. And we can keep on going to see what the equivalent of something, a p-value even smaller is, and you can see it drops off quite quickly. 65, 66, and now we're at 0.001, or just under, and that is the equivalent of 66 heads when we flip a coin 100 times. So that's what it actually means in practice. So have a think about that when you're thinking about your p-values, and it's a good way of working out what it actually means when we see this p-value in practice. Now, since this is a series on JASP, maybe we should have a look at JASP and see if it can actually help us, and it can in terms of viewing this distribution in terms of a probability distribution. So for example, if we go to the show module menu, you'll see that we do actually have a module on distributions. So if we look at that and look at the distributions, as I said, I'd taken a few liberties in terms of this example, and what we need to look at is what we call a binomial distribution, which is what we are using essentially by doing flipping heads and tails using a coin. And so we can actually illustrate this by setting our experiment up in the same sort of way. So again, we can have a look at the range and the cumulative probability, and if we have a look at the value we looked at in the previous example, which is 59 to 100 in the first instance, you can see there's our p-value 0.04, and we're actually looking at this small amount of area. In actual fact, it's the area all the way up to 100, but of course in typical fashion these probability distributions tend to go down to very small values as you go further and further away from the central value. So again, we looked at this approximation of a 0.05, and we also looked at, I think it was 65 we looked at, and again JASP will do that calculation for us, and you can see 0.002 in that particular case, and it's absolutely tiny, it's down here. So this gives us an indication of what that p-value means in practice. So again, you might want to have a look and use JASP from this point of view to play about with these numbers, to give yourselves a feeling about what these probability distributions actually mean in practice. So I'm hoping that's been helpful.